And welcome to the third video in our discussion of analysis of variance. So in the last video we completed our analysis of variance, our ANOVA, and we determined that the effect was significant. In other words, that the instructions for the different types of homework completion, whether it was required, optional, or extra credit, was significant. However, as I indicated at the end of that video, the fact that it was significant doesn't tell us which level of the IV had an effect. Did they all differ from each other? That is, did they all come from different populations, or only one, or whatever? So post hoc test. Post hoc means after the fact. After we get a significant ANOVA, we can then go in and dig a little bit deeper and find out where those differences lie. So on the screen here, I've shown you the means of the three groups. We have our, let's see, this was the homework that was required completion rate with a mean of 21. We have the homework that was extra credit, and that mean was a bit further away. That one was 14.8. And then we had the optional homework, which was way far away. Only 6.6 people on average completed those assignments. So that's the way things kind of look, and our the next step is to figure out if these all came from the same populations, there's some massive population that they are all a part of, or are they all parts of different populations. So let's clean this up a little bit and show you the post hoc tests. Okay, we're all cleaned up. So there are actually many different types of post hoc tests. The difference among them rests on some of the assumptions that they make and how much they protect us against type 1 errors and so on and so forth. And you'll read about a little bit of those details in your textbook. The version of post hoc test that we are going to use in this class is called the honestly significant difference test, or the HSD. And the formula is on the screen there. It's also on the slides. And you'll see a new letter in here, Q. And you might ask yourself, what the heck is Q? Well, Q is a value that somebody a lot smarter and nerdier than I came up with. It's actually lots of different values based on some of the parameters of our analysis. And to find those, you're going to turn to table Q in your textbook. And if you look at that, you'll see the table actually looks fairly similar to the ANOVA table. However, it's based on the values of, here, let me put it up here. So Q is based on the degrees of freedom, or not the degrees of freedom, excuse me, the number of groups and the degrees of freedom within groups. So if you look at the table across the top, you'll see all of the K's, 1, 2, 3, 4, and so on. And along the bottom, we have, or along the left-hand side, is the degrees of freedom within groups. And there will be 1, 2, 3, and so on. Well, we had 12 degrees of freedom within groups. We had 3 groups total. So there's the 3, there's the 12. Where those intersect, we can see that our critical, or our Q, is going to be 3.77. So that's the Q for the formula. Otherwise, everything else looks pretty good, or pretty similar. I'm going to move this formula aside, and so we can complete our calculation of this value, the honestly significant difference. We're going to take 3.77 and multiply that times our the square root of our mean square within groups. That's the variance within groups, which if you look back at our ANOVA summary table was 7.5, divided by lowercase n, the number of individuals in the group. And when we do that math, we come up with 4.618. Hopefully that all fit in there. That 4.618 is now a critical value. It's the the difference between two means that is required for significance. Anything greater than that, we say that that difference is significant. Any less than that is non-significant. So let me clean up the page here. All right, and move this up just a little bit more. Give me some space. And we calculated that HSD, the honestly significant difference, to be 4.618. So now we just walk through all of the possible pairs or comparisons of our means and see if they are larger than that critical value. So if we compare our required group right here to the extra credit group, which is right here, if we take 21 minus 14.8, we get a difference of 6.2. There's a 2. Well, 6.2 is greater than 4.618, therefore that difference is significant. In other words, when homework was required, there was a significantly higher completion rate than when the homework was offered only as extra credit. So that's comparison 1. We'll change colors and go for comparison 2 now. Let's compare, once again, required homework that had a mean of 21. And look at the difference between that and when homework was merely optional. And that score was 6.6. That was the mean score there. Well, 21 minus 6.6 is going to be 14.4. So obviously that is larger than 4.618. So that is also significant at the 0.05 level. Just like required versus extra credit, if you make homework optional, you're going to get significantly less or fewer people completing the homework than when it's required. And our last comparison, new color, we're going to compare when homework was made for extra credit, which is the mean for that was 14.8, and find the difference between that and when it was optional, which was 6.6, and the difference is 7.8. 7.8 is also larger than 4.618. Therefore, that is also significant. Making it optional results in less or fewer completions than when it's offered for extra credit. So now we have finally completed our ANOVA start to finish. We found that overall the variability between groups, between the required extra credit and optional groups, was more than just the individual variability within groups. And from that, we rejected the null and we inferred that our manipulation caused some kind of change in homework completion rates beyond what we would expect just by normal variability from one person to the next. We then completed the post hoc test, in this case the honestly significant difference approach, which told us that all three groups differed. In other words, we are assuming or inferring that all three of those groups come from different populations. The required group behaves differently than the extra credit group, and the extra credit group behaves differently than the optional group, and so on and so on. So from this, if I was an instructor or a professor, I might say, yeah, it's probably best if I make homework required because I'm going to get more people completing it, and if I believe that completing homework gives you good practice and mastery of the material, then that's what I want to achieve. So that is an analysis of variance start to finish. Now you'll read in your textbook, and actually on the slides, where I want you to, or I show you how to write the results of the experiment up. And so I'll read that to you now. It's actually slide 19 if you're following along there, where I concluded that an analysis of variance comparing required, extra credit, and optional homework completion rates revealed significant differences among groups. And then I show you how to write up the results of an F-test. And what we do is we write that it was an F-test with 2 degrees of freedom between groups and 12 degrees of freedom within groups equals 34.333, and the probability of getting an F value that large by chance alone is less than 0.05. Okay, that's the official way in the social sciences, at least that's the APA way of writing up the results of an ANOVA. I continue on with the summary paragraph. Post hoc comparisons using the honestly significant difference method showed that requiring homework yielded higher completion rates than both extra credit and making it optional. If you remember, those first two comparisons were significant. Continuing on, further, offering extra credit resulted in higher completion rates than when homework was optional, period. So that little paragraph summarized everything. I told the reader, if I was presenting the results of my experiment, that we did an analysis of variance. I told them what the groups were that we were comparing, and I told that it was significant, and gave the statistics that I'm basing that conclusion on. And then I described the post hoc test and what the specific results were. So that's kind of the way that it would be written up if I was writing this into a professional journal. Okay? So to summarize then what an ANOVA is, the last slide in the lecture notes, an ANOVA is a way of comparing more than two groups. If we just had two groups, we could use a t-test or a z-test if we have all the population parameters. But with more than two groups, we have to do a little bit more. The bottom line is to compute the mean square between groups, that is the variance between the different groups in our experiment. We compute the mean square, or the variability within each group. We have to pool those, average those together. And then we create a ratio. That ratio of between groups variability to within groups variability is testing the null hypothesis. The null hypothesis says that both of these are just measures of error. If our independent variable had no effect whatsoever, then any difference between groups is just sampling error. Why one sample differs from another taken from the same population. Just like why one person differs from another when taken from a population. So if these are both measuring error, then that ratio of between to within groups variability should be fairly similar or fairly small. But if our independent variable is having an effect, that is, if the groups actually come from different populations, then the group means should be further apart. There should be more variability than we see just by individual sampling error. And as a result, the larger the F ratio, the more likely or the more rare that finding is, and the less likely the null hypothesis is true. So if it passes some critical value, we reject the null hypothesis. And from there, we have to do post hoc tests to determine precisely which of the means differs from which. It might be all three, like in our example, but it might be only one is different than the others, and we don't know which one, and so on and so forth. So we use the honestly significant difference method. There are many others out there, but for our purposes, just focus on that one. It's a fairly simple, straightforward calculation. We'll look up Q in the table and multiply that times that little bit of the formula where we take the variance within groups divided by n, take the square root, etc., etc. All right, go back and review that if needed. And that's an ANOVA, start to finish. So hopefully this gives you a good understanding, and we will see you at the next topic.